So it's a great pleasure to introduce Pei-Lun Tseng, who will give the tutorial for free probability theory. Thank you, Pei-Lun.
Thank you very much. So this one?
Yes.
Figure it out. Okay. Yeah. Hello, everyone. It's my pleasure that I can share some knowledge about free probability, some basically like a structure and some example. Okay. Many of the material you will have seen, I mean, in the morning talk from Jamie, and but now I try to give some example and try to compute in them. Okay. So this one. Okay. Yeah. Oh, sorry. Yeah. Okay. So the very basic framework of free probability, we're starting from a phi. It's a pair, and which we call it non-community probability space. And where what's the A? A is just a unitary unitary algebra and over C. And the phi will be a linear functional, which is sending the A to C, and we assume that phi should sending 1 to 1. But now I try to give some more concrete example. Okay, first, what's some example? It could be like the first one. How about we back to the classical probability setting, and we consider the space. The A we can choose in by L infinity. Yeah, it's very clear like a L infinity space. It's also a algebra, including the element 1. And but for L infinity space, we don't have something called moment distribution. I mean, moment is not a boundary, so we can make it like a little bigger. Then usually we call L infinity negative, which is divided by, we consider all the LP space, and we do the intersection. Okay. Okay, for such space, it's clear it's an algebra. And what's the probability state we should use? I mean, what's a proper phi here we can use? There's a pretty natural way. We're just choosing the expectation. Okay, yeah, that's the first example. So for this example, you can see, even though we say it's a non-community, but actually in this example, the model is community. You have, if you're given two random variables, x, y, x times y is equal to y times 2x. So for the setting we are here, we say non-community probability space is the same. We're not forced it's non-community. We just say it can be non-community. So how about the second example? Then we really given a non-community example. Then we consider A is and C. Just a complex n by n matrix.
Sorry, is L infinity minus an equation? Is it an algebra?
Huh?
Is the second one an algebra?
Yeah, we force. I mean, it's intersection of OLP. So if you have two elements, and if you sum, you do. Yeah. We force is intersection. Yeah. It will be algebra. Okay, so for the second example, we're given a really non-community example. So if you have two random, if you have two matrices, we know like A times B, it may not be B times A. So this one is non-community. Okay, what's a proper way we given a proper phi for this model? We will hope the phi is linear and ascending 1 to 1. So there's a very good option. It's called a trace. But if we do a trace, then we know we're given a matrix model, especially if we consider 1, which is identity matrix. When we plug in identity matrix, this one gives you M. It's not 1 anymore. So what we were going to do, we just normalize it. Yeah. Okay. So let's two simple model for the non-community probability space. How about we combining both of them? We just mix them. Then we got one random matrix model, which is M. and we plug in the A here. So maybe we say L infinity negative. Okay. So now we have a model, which is n by n matrix, but each of the entries is not a complex number anymore. It's a random variable. And so for such model, the phi is also clear. We will mix these two phi together. So we will do 1 over m. Trace. Okay, there are 3 simple models. Okay. Now, when we have a non-commutative probability space, the next thing, for a given element, we can collecting all the possible moments and do something, formal power series, formal Lorentz series. And this guy we call a Cauchy transform of A. Yeah. So here we all of the form are formally defined. Okay. And when you have the Cauchy transform, and let's way, we just computing the inverse composition of a GA, and we got something called GA inverse. It's another formula. For this guy, if we subtract 1 over Z, then we will call the R transform. R transform. Yeah. And you can observe that R transform can be written down by also a formal power series. And such coefficient we will call a free cumulative sequence. Okay. Yeah. So that's very abstract. So let's try to compute in some concrete example. This should be this one. Okay. Yeah. Oh, it's a composition inverse of GA. Oh. Yeah, this one. Yeah. So when you give an A, you can compute in the moments.
It starts with 1, so we can take this. No. Okay.
Yeah. This when n start from 0. So actually we're starting from 1 over Z plus phi over Z square and so on. Yeah. Yeah. Okay, and then let us computing some concrete model. And this model actually is play a very important role in free probability theory. Okay, so for a given non-commutative probability space, also, by the way, NCPS is an abbreviation for non-commutative probability space. And we starting from a given element. We call such an element is a semicircle element if it satisfies a rule, which is the moments of such element will follow in the semicircle law. Okay. So when we have these things, if we want to really understanding this semicircle law, we want to catch, okay, what's the cumulant is, what's the R transform. So if we want to catch R transform, we want to understanding the cumulants. We have to starting from by the process we see from previous slide. We were starting from the Cauchy transform. So first Cauchy transform, we were starting computing the moments precisely. Okay. So in order doing that, first thing we can observe, when n's r is trivial, that the other moments are okay. Yeah. But for the even case, if we letting n equal to 2k, then we can start to computing this one. Yeah. We do like a triangular substitution, then we can see easily it can be written by this way. And since psi square is 1 minus cosine square, so then we can rewrite it by the ik minus ik plus 1, where each of ik is this one. Yeah. Yeah, some basic calculus. And based on this, now we try to study this guy. So, sorry, there's something in chat. It's okay. Yeah, that's okay. Let's skip it. Okay. So then we try to catch up these things. So then we just observe one thing from the first 2 lines. Cosine 2k theta can be written by the ei theta plus e minus I theta, and we put in the 2k outside. And then we using the like a polynomial, and we write it as binomial polynomial. Yeah, polynomial. Yeah, we write it by the right hand side, and we observe one thing that if we focus on this guy and we do the integration from 0 to pi, it's only survived when L is equal to 0. Yeah. And hence, then when we solve that form, if we do the integration, only wherever j equal to k will survive. So the ik will be exactly this one, and all other term will be killed. Yeah, and hence, if we back to this formula, then we know from previous slide it's 4 to the power k plus 1 times the ik minus ik plus 1. But ik minus ik plus 1, we know precisely is this guy. And we just combine them together. We can see a formula like this. And for the last part, we just dividing 1 over 2 pi. Yeah. Then we got what's the field of A to K, which is this form. Then it's like a well-known guys. It's called like case Katara number. Yeah. And we got the Katara number here. Yeah. Okay. So now we have the moments. We want to know more. What's the Cauchy transform? So we go further. So we're starting from the Cauchy transform, and we write it formally, and the phi an now we know precisely. It only surviving when n is even, and it's a Katara number. So we just write it precisely as a Katara number. And that's a very important property for Katara number. The ck is precisely can be written by the sum of the j from 1 to k, the c j minus 1 and the c k minus j. Yeah, and now we can observe here we have two sums. Then we just for a z 2k plus 1, we just split by 2 part, half of them for the cj minus 1, another half for ck minus j. Now we do the interchange of the sum for this state to here. But after we done the interchange, we can see this one is precise. It's a Cauchy transform. And after we rewrite this one as a Cauchy transform, then this another guy is also the Cauchy transform. So which means we got the Cauchy transform G is equal to 1 over Z plus 1 over Z GZ G squared. Now we got a quadratic formula for the Cauchy transform. Yes. Yes. Yeah. So now we have a Cauchy transform formula. Now we try to understanding, okay, what's the precise of the GZ looks like. So now let's move on to the next page. So when we have a Cauchy transform, then we can use in also a quadratic form, so we can compute it precisely. By then you can see it's just z plus minus root z squared minus 4 divided in 2. Now we have two options. We can choose in plus or choose minus, but which one is the proper one we should choose? So here actually somehow I have some cheating. Since all over here we do the algebraic label, but if you go into the analytical label, and we have the great orange part, we have such formula. So if you based on the orange formula, we know the negative one will be the one we should choose. Yeah. Yeah. So I mean, go to the analytical version means we consider starting from a compensable measure. So. Yeah, it's starting from a measure with compensable, and the Cauchy transform will be considered as this way. And of course, we need to consider the z such is well defined. So usually we will consider it's on upper half plane, and based on this formula, and since it's compensable, you can return this one as a power series again. And it will coincide with the formula as algebraically version. And furthermore, for the analytical version, you can prove the orange part. Yeah. So that's why when we have the plus and the minus, these two options. So by the analytical theory, we will know, okay, we should choose the negative one. Okay. And as long as we have the Cauchy transform precisely over there, then next thing, we want to catch up what's the R transform. So first, we have to compute in the composition inverse. Right? So for the composition inverse, we letting the GA equal to W. Then we just invert computing them. Actually, the formula is very simple. The GA inverse just exactly Z plus 1 over Z. Now the R transform is divided by G inverse minus 1 over Z. So R transform will be nothing but a Z. So you can see from the beginning, it looks very complicated. But after you go through all this process, eventually R transform is very simple. Yeah. And when you have R transform and you try to return by a formal power series, yeah, over here, then we can see the corresponding coefficient. The first guy, kappa 1 is 0, kappa 2 is 1, and all other are 0. So we got the corresponding coefficient kappa m, only surviving when n equal to 2, and all other will be killed. Yeah. Okay, let's have one direction we can do in this. But how about we using the partition to study this stuff? So, okay, so let me quickly recall some partition stuff. Yeah. So when we're given an m, when we're using this parenthesis m to mean a set 1 up to m, and we can consider, okay, the general partition on m. Then we can consider another called non-crossing partition on m, which is satisfy this rule. I mean, if they don't exist a case, the ij, lk, such that IL in a block, JK in another block. Yeah. So, okay, I can draw some. Okay, so when you're given a pi, now you have I, J, LK. Yeah. Then if IL in a block, JK in a block, which means they were crossing. Okay. In the sense, then there's a meaning what we say the crossing. So if this is not going to happen, we say this partition is non-crossing. Okay. Yeah. And another notation, if all the non-crossing partition, each of block only containing 2 elements, besides 2 elements, then we say it's a non-crossing period. We're using the NC sub 2 to represent this set. Okay. Yeah. And for the non-crossing period, there's an important fact. Is if you consider the number of, for a given m, what's the number of a non-crossing period? Will be precise of the Cartesian number of n over 2. Yeah. So over here, of course, n should be even. Yeah. If n is r, there's no chance to have a non-crossing period. Yeah. So I didn't write that down, but n needs to be even for sure. Okay. Now I just write down the few examples here. So over the first one, you can see the graph. If we have the 6 elements, and 1, 2, 4 is in 1 block, 3 is a singleton, 5, 6 in a block. Now we have 3 blocks. But you can see the graph is non-crossing, so it's in the NC6. But it's not a period. Okay. How about the second one? This one is obvious crossing. So this one is in P6, but not in NC6. And the third one is also non-crossing. But we have 2 singletons, so it's not all period. So it's in NC6, but not in NC26. Okay. And the last one is the case is non-crossing period. Yeah. Yeah. Okay. Okay.
Sort of understand the importance of this G, because it's like trace of the resolver, more or less.
Trace of a resolver. You mean the Cauchy transform?
Yeah.
Mm-hmm.
You write it in geometric series and
Yep.
you get that. What is the importance of R?
Yeah, of R. Yeah, the R. Yeah, you will see the. Okay. Yeah, you will see maybe right away. Yeah. Yeah. So right now, if you focus only one element, it's not easy to see what's the R play the role. But if you have 2 free random variables, yeah, I will play the important formula. Yeah, we will see right away. And at the end of this talk, I try to prove the central limit theory by using the R. Yeah, will be almost straightforward in the one line proof.
You could say that the way to think about R is just wrong. It's like if you were to take a constant probability characteristic instead of Cauchy transform, it's It's not actually, but it's the analog. I don't know if that's the type of heuristic you want. There's no analog in if there's the log of the characteristic. Yeah, so it's a different relation between different functions. The keys, yeah. So yeah. So it's like just not. If you're looking for a heuristic.
Yeah, I'm just looking for some heuristic. Thank you.
Okay, thank you. Let's keep going. So now if we given a non-community probability space, then the first few lines just a notation. And if we have a family of a multilinear functional, we call it FM. Yeah. Then for each pi, for a given pi and a given some element, A1 up to M in A. Then the F pi of A1 up to M, we will divide it by this way. Okay. Yeah, it means for each block, we just consider F of the size of a block. And also the corresponding element, we just plug in into the function. Yeah, and then we just consider product of them. Okay. So it's a little vague. I give an example here. Okay. If a pi is such guys, it's 1 up to 6, and we know 1, 2, 4 in a block, 3 is a singleton, 5, 6 in another block. So 1, 2, 4 is in the same block, so we have F3. Since we have 3 elements here, and the corresponding guy is A1, A2, and A4. And the second block is a 3. It's only one element, so we have F1 here. And the corresponding element is A3. And the last block is 5, 6. So the size is 2. And corresponding element is A5, A6. Then we just tie multiple overlap together. Then this guy we call the F pi. Okay. Yeah, just a recall from the Jamie's note. Okay. Yeah. Jamie's literature. Okay. And then after this, we can define what's called a free cumulance. We will define in really based on this formula. We call a moment cumulant formula. So cumulants will be the family of a multilinear functional. Yeah, and we will define it based on this formula. Okay. Yeah. So I think it's a thing, and then we will use it. So this slide. Okay, so yeah, as I mentioned, I will try to give another approach to prove for a semicircular element how to compute in the cumulants. Okay, so I just give a simple notation here. If we consider, we see before, if we consider phi A1, A2 up to AM, or if all of them are the same, it's just phi A, then we just say phi AM. Then this is just a moment of A. We're using the notation NNA. And similarly for cumulants, if kappa M, the all inside guy is A, then we just call kappa NA. Okay, it's called free cumulant of A. Yeah. So as we saw before, if we have a semicircular element, then we can compute it precisely. For a semicircular, the corresponding moments is this one. Yeah, when N is even, it's Catalan number N over 2. N is R, it's 0. How can we find this information? And using the moment cumulant formula, we saw from previous slide, to catch up, the kappa NN is exactly the same we computing before. Okay, so let's see the proof. The proof is, we observe first, the kappa 1, what's the N1? N1 is summing up, or maybe I just write down formula here. Yeah, we know based on this formula, if we consider N1, the non-crossing partition only have one element, which is kappa 1. So N1 is kappa 1, so it's nothing different. N1 is kappa 1, but we know that N1 is 0, so we force kappa 1 is 0. But how about N2? N2 is kappa 2, and N2 if we have NC2. Now we have two options. It can be 1, 2 in the same block, or we can have the 2 singleton. Okay, so in this case, will be kappa 2. In this case, it's kappa 1 times kappa 1. And hence we have the N2 is kappa 2 plus kappa 1 squared. But we already know the kappa 1 is 0. And then by this formula, we can see kappa 2 have to be 1. Okay. Now, if we keep going, we just can see, actually, I also skip for the n is odd. N is odd is simple. Okay. For, okay, let me keep going. Okay. For even n, we know like n is a Cartan number Cn over 2. But on the right-hand side, we have a moment cumulative formula. For the moment cumulative formula, we consider all the possible pi in non-crossing partition, NCM. But now, how about we split by 2 parts? One is a non-crossing pairing. One is a non-crossing partition, but not pairing. Okay. For the non-crossing pairing part, we know all the form is 2 element, 2 element, 2 element. And each of the 2 elements will providing kappa 2, kappa 2. So we have lots of kappa 2. Each of the kappa 2 is 1. So we just 1 times 1 times 1. So we just get 1. So actually here we sum it up all the non-crossing pairing with the value 1. And hence it's just exactly the size of the non-crossing pairing. And we saw before the non-crossing pairing actually is Cn over 2. So we saw this formula, we saw one thing. Left-hand side is Cn over 2, right-hand side is Cn over 2 plus something left. So which implies this stuff, the left thing is a 0. And if you saw this is 0, now it's easier. You just start to check it. When n, you plug in 3. Actually, plug in 3, this is nothing but 0. But if you consider 3, then this guy, you write it down, is all of this. You can see only all the element is containing a singleton. So we'll force it to become 0. So all of them are 0. Then which force kappa 3 is also 0. Now if we go to another n equal to 4. So we have a kappa 4 and a plus last thing, but cannot be pairing. If it cannot be pairing means each of the kappa will contain kappa pi will contain a singleton or some element with 3 elements. Then we'll force each of them will be 0 again. So we just go this process. We can see all of them will be 0. Okay, yeah, let's sketch over proof. Okay, then, sorry. Okay, let's move on to freeness. Yeah. Okay, so for the freeness, maybe first let me recall the definition. Okay. If you have a few subalgebra, are you using n? Using n? You say they are free. Subalgebra. Are free. If okay, so we say they are free if we have for any k, and we consider the index set I1, I2 up to ik, and each of them is from 1 up to m. Okay, then we assume okay all the index set I1 is different than I2, I2 is different than I3, which means all the adjacent elements from different algebra. Yeah. But in this definition, we don't really care about I1, I3. They came from the same algebra. Okay, but just the different. I1, I2 needs to be different. I2, I3, and the ij plus 1. Okay. And for each of the aij, we're choosing an element aj from the aij, and we force it to be centered. And under this definition, we want this thing happen. Phi of A1, A2, up to AK, I think is 0. Okay, that is a definition of freeness. This one can be used to manipulate to use this definition to computing the mixed moment. Okay, so how to use this one to compute the mixed moment? Maybe let me quickly show some example. Okay, let's the first one and the second. So let's freeness of subalgebra. How about freeness of 2 elements? We say 2 elements are free if all some elements are free. If an algebra generating by X and algebra generating by Y are free. Okay, so definition of the element of free is just based on the definition of algebra generating by x and y. Okay, and now maybe let me quickly quickly catch up the very simple example. If you have x, y, they are free. You know, like for the classical independent, it plays a very important role to understanding how to compute in a mixed moment. So over here we can see, okay, if they are free, whether we can play the same game and to see how to compute in the free xy. Yeah. And based on this definition. Yeah. So first, if you want to compute in these things, but if we want to use in this definition, all of them needs to be centered. But here, they are not centered. So we can do something. We just consider this one. Oh, sorry. Let me using AB. XAB. Okay. So we can consider this one instead. Yeah. So let's observe. This is VA1 to be more precise. VB1. Yeah. So VA is a complex number type 1. Okay. So this guy is A minus VA1. This one is B minus VB1. And if you consider phi of this one is 0, and phi of this one is 0. Okay. So by this definition, 0. And based on this, okay, if you want to, then if you expand in them, they totally have 4 terms. You can do some cancellation. Then you can easily see VAB is VABB. Yeah, it's exactly the same as classical setting, classical case. Yeah. Sorry, here's AB. Yeah. So of course we can go further to consider what's the VAB-AB. And so on. Yeah. So over here you can see, you may guess, oh, it's just the classical independent. But actually, when you consider AB-AB, it will be little different, very different. Okay. And but usually the way we computing, we will based on the same formula. We can do it again, but it's many turns. So how about we change a way? We have other way to doing this by using the cumulant we just see before. Okay, but if just using the cumulants, you return as a sum. That's the now we have a 4 element, so it's NC4 gamma pi of AB. Okay, will be this one, and we want to catch up all of them. It's still many terms. We can see the NC4 still have many terms, but that's one good thing. We assume they are free. Then we can back to see this formula here. That's a very important result for the cumulants. If with some subalgebras they are free, then it has an equivalent condition for the cumulant. It's saying that the kappa n of A1 up to An needs to be 0, as long as not all of the A1 up to An from the same algebra. Okay. Yeah. So this one can be understanding as this sentence. Okay. Freedomness is equivalent to vanish of missing cumulant. Yeah. So as long as you consider the cumulant and A1 up to An, if they are not from some AS, then the kappa n should be 0. Needs to be 0. Okay, then let's try to see, based on this formula, whether we can really quickly solve this problem. So I erase up. Okay, so maybe you can list all of them. NC4. So what's the first one? This one. And we can have a 3 and a 1. 3 and a 1. 3 and a 1. And 3 and a 1. And yes, 3 and a 1. Now we have 2, 2. 2, 2 can be this one or can be this one. And that's for 2, 2 and 2, 1, 1. 1, 1, 2. 1, 2, 1. 1, 2, 1, 0, 1, 1, 3. And Okay, 1, 2, 1, 4, 1, 3. And, I think, yeah. Make 2 of singleton. 2 of singleton. 1, 3. Yeah. Okay, thank you. Okay, I think we're almost done, right? Then 1, 2, 3, 4. What else? Do I miss anything? 1, 4 is yes, thank you. I think let's say it, right? 2, 4. No, I think this one we have already. 3, 4 as a singleton. Yes. Thank you. That's everything, right? Yeah, 14. Yeah, correct. Okay, so now let's based on this way. We know it's AB. So here is AB. So AB in the same block, according to the formula we have, it needs to be 0. Let me change your color. Kill. Then ABA. So we mix the A and the B. Kill. So you can see, as long as we have 3 elements, then there's no chance to survive. So you can kill lots of things. AB, kill. AB, kill. AB, kill. Yeah. AB. Yeah, survive. Kill. All right. You can see, it looks like we have to sum it up so many times, but eventually we only sum 3 things. And what's they are? So they are, these 2 are kappa 2. So it's kappa 1a square, kappa 2 bb. Is this one? And another one is kappa 1 b square, kappa 2 aa. And last one is kappa 1 a square, kappa 1 b square. Yeah. And then now we also know some note. The kappa 1 is N1, and the kappa 2 is variance, which is N2 minus N1 square. Okay. So we can be writing this one. So maybe I jump to the result. So after you done that, you will see it's A square phi B square outside plus phi A square outside B inside minus both outside. Yeah. Sorry, which one? Which one? Sorry. Oh, you mean this one? Since AB in the same block, it's kappa 4 AB. And in this formula, as long as A and B in the same kappa, they should be 0. Yeah. So that's a very poor way. But okay, so on one hand, we know the phi AB is this formula. Yeah, it's this formula. Let's by Friedenus. Okay. And now we can ask him a question. If it also AB are classical independent, what's going to happen? So if it's also classical independent means this one, we know classical independent means they are commute. Here will be phi A square B square, and we can divide by phi A square phi B square. If it's true, independent. Now we have a formula that this one equal to this one. And if you combining them, then you will see a very cool thing. It's phi A square minus phi A square times phi B square minus phi B square is 0. But what we know, this is positive, this is positive. 2 positive things tied together is equal to 0. And fourth, one of them needs to be 0. But what's the meaning? This one going to be 0. It's a variance. So variance is 0. Then it only can be constant. Yeah. Okay. Yeah. So that's why for a model, as long as the A and the B are at the same time free independent and the classical independent, only whenever one of them needs to be constant. Okay, so now we back to here. Okay, let's sum it up. Okay, now let's back to here. We give a small note. So if A, B are free, and we back to the R transform. Okay. Okay, RA plus B, we know, okay, we just write down as definition as this way. And about kappa n plus 1, we know it's multilinear. So it can be written by several terms. Yeah, we have the term which is kappa m, all of them are A. And another term is all of them are B. And we have a last one missing term, A and the B are missing. Okay, but we know A and B are free. So false, the all the missing term will disappear. Okay, so eventually, RA plus B is nothing but RA plus RB. Yeah, it's a linear. Yeah. Okay, so. Yeah. Yeah, we just observe our conditions from it's hard to see how can we understand in the X plus Y. Yeah, but if we invert to R transform, it's very simple. Yeah. Okay, so for the last slide, we try to using this formula to catch up the free central limit theorem. Okay. So for the free central limit theorem, since we define algebraically, so we starting from a non-commutative probability theory, space, and we given several of elements. We assume they are free, right? And we assume also they are identical distribution. So which means all of them share the same moments. Right? Now we further assume they are center and the variance is 1. Just do some normalize. Okay. And based on those assumptions, we consider the SM, which is 1 over root n of A1 up to AM. Right? And we can prove free central limiting theory saying that the SM will converge to a standard semicircle law. Okay. So since here we are saying in algebraic sense, so means that the field of SNK, okay, the moment of SNK will converge precisely to the moment of standard semicircle law, which is this one. Okay. Yeah. Okay. So how to prove it? It seems very complicated, but now we have R transform, so it becomes very easy. So we're starting from under RSNZ. Okay. And we know Sn is precisely the 1 over root m of A1 plus up to m. Now here I'm missing something. Okay, let me quickly show. Since R transform is multilinear of alpha AZ, by the formula we know it's kappa 1 of alpha A and plus kappa 2 of alpha A of Z and so on. Okay. Kappa m plus 1 alpha A, that's of alpha A and Z to the n. So here m plus 1 times. Okay, so now we know that each of the kappa are multilinear, so we can pulling out the alpha. So for first one, we're pulling out alpha. Here we're pulling out each of them. We can pulling out the first alpha. So we will get alpha of kappa 1 of A. Second one, we just merge the alpha with Z. Okay, we do the same thing. We're pulling out 1 alpha. Now we remaining n alpha. We just merge with Z. So we got the formula. Okay. Oh, sorry. This one is unlimited. Yeah. So we can see, okay, what's this one? It's exactly the Cauchy transform of R, RA, alpha of RA. But the inside guy we choose is alpha Z instead of Z. So it's alpha Z. Yeah. So we have this formula. Okay. So this is the second line come from. So if we have this one, we just pulling this out, 1 over root n. And another, we have to replace the z by 1 over root n z. Now over here, we're up to here. We assume since they are free independent, so will be a sum of RA1 plus RA2 plus up to RAM. Each of them have the same distribution. So all of them just RA. Okay. They are the same. Okay. But we repeating n times. So now we just have n times 1 over root n. So we got root n here. Now we just expanding RA precisely by the cumulant. Oh, sorry, by a power series. Then we can observe here. Over here, kappa 1 is nothing but the first moment. Yeah. But first moment, by our assumption, phi A1 is 0. So this guy K is 0. How about the kappa 2? Kappa 2 is a variance. So it's n2 minus n1 squared. This one is 0 again. So this one we know is 1. Second moment is 1. And how about the remaining term? We don't really care because you can see here it's root n to the 2. So it's 1 over m. And then so on, the power will getting bigger for the denominator. But from the beginning, we only have root m. So when root n ties over all of them, and the root n will cancel over root n. So we got z here. But how about remaining 1? This one will tend to 0, where n tends to infinity. So eventually, we only got something called z, which is 0 plus z plus 0, 0, 0, 0, 0. Yeah. So then we catch up the free cumulants for the semicircle law. Then we have a moment cumulant formula. We can invert back to gather the moment. Yeah. So yeah, that's a very very standard way, and also a very very cool about the R transform. Yeah. And that's it. And the last thing I want to mention, you can find all this material from the Endo and the Lawrence book. It's very organized, very good to read. Yeah. And thank you for your attention. Conversion rate, yes. Will be very some analytical approach, yes. Yes. Yes, there's something called free Brownian motion.
How do they construct it?
They're starting from, I think, the finite von Neumann algebra, if I remember correct. And then the thing is x plus xi minus xj is not the same, considered as a normal. Yeah, it will be considered semicircular with a variance by the difference of the r minus s. Yeah. And then we not assume they are independent. We assume they are free independent. And we can.
What is that the process is? Yeah, it's time parameter, and then the increments instead of asking them, and then you ask them to be independent. Yeah, and then this would be the definition, and then you have to prove it exists.
Yes.
Yeah, and also the distribution. So if you take different times, the distribution of the difference should be semicircular of suitable variance instead of Gaussian. Yeah, and you prove it. Yeah, I think it's Jan and Speicher.
Yeah.
So, or maybe even. But Jan and Speicher really do integration against the Brownian motion. So they do like stochastic out.
Is there now, so I can ask the next question. Is there any analog of free Gaussian field?
Free Gaussian.
Random surfaces.
That one's a little.
Yeah, this would be for future. I asked Jamie some.
It's the same answer.
I think this would be wonderful to pursue. There's a lot of activity.
Gaussian.
Vigorous activity.
even some attempts to make some that connected to the trend.
Yeah.
So it's not really.
What do you mean in the free variant? Okay, very good. So, any other question?
Previous it's
What,
the
sorry?
same. You asked about convergence rate.
Oh, convergence, yeah.
Convergence
The
rate.
large deviation.
Square root of n. Convergence theorem only depends on its absolute moment. In case you need to. Assignment.
Yeah, so then there's some large deviation theory.
We put free in front of a lot of things.
It seems that's the way it was developed, actually.
Very seen, right?
The same square root of.
The very seen inequality.
Oh, yeah, this
Exactly control the
convergence rate.
without.
Thames also, yeah. Are there any other questions?
I mentioned brings the cat.
This guy is out, right? Hey, they hear us at all?
Yeah, we
They hear the questions. Oh, okay.
Additional information you're asking.
Using some all freeze. Also. Just there are one. Okay. Always. Okay.
So probably asking about.
When you use about as time goes on, the subalgebra is larger or random variable. Right. You don't talk about algebra. Expectation. Yeah, taking 5 and a conditional. Okay.
So conditional expectation.
Sorry. The general theory, I think Nakasaki.
Yeah, already there. Yeah, that's right.
That's well, when you take conditional expectation and what the modular on. But finite case, modular on trivial. So and then ratio trivial. So always.
There are some things you can't. There's no 3, 0, 1. Just so that you know it's not everything.
It's all trade-off.
Also free for.
Feel one rule.
Yes.
Okay, are there any other questions? So before we thank Pei-Lun, let me say again that have wine and cheese, courtesy of my department. All of you are, of course, invited because of you. So it's at 6 p.m. So they have to set things up and stuff. So we have like 25 minutes free, and we can then go into wine and cheese. Let's thank Pei-Lun for a great talk.
Thank you. Stop sharing.